All right, so I just sent an announcement out on Canvas, and you may have gotten an invitation to a Zoom or a Big Blue Button conference, our Canvas conference. And so what that's all about is in some of the emails that I sent out a couple days ago, I got some feedback back where students said it'd be great if there was a way for them to have some sort of study session so that before, like say now in the final exam, that maybe they could get together with students and share any concerns and try to help each other with any problems that they're having with the concepts. And I'm going to ask Taha if he can also make some time for something like that, for something more centralized. But on a decentralized perspective, I thought it would be great if I just helped you facilitate finding each other. And so I've created on Canvas, if you click on the conferences link on the left-hand side, there is a conference that is running right now, and this is different than Zoom. And so that way it doesn't have to be tied up to a Zoom's like host ID. It's a different video conferencing service with a lot of similar features as Zoom. And then I've also in the announcement put out a when is good poll that allows people to go in and then just fill in their availability and then also view everyone's shared or combined availability. And so the thought is that if there's a bunch of you that you're interested in this, you could go in, put in your availability, and then go and maybe a day or two later, check what people have entered. And if you see that there's certain spots that have a lot of people who are available, then you could put something in the discussions, or you could send something out in the people in Canvas that says, hey, we're thinking about getting together at, at 5 o'clock on Thursday to discuss, SOS 212, or maybe even other courses that you're taking together. And then it's a way for you to then find each other and not have to like send a bunch of emails around. And so it's just supposed to make it a little easier for you to form these groups. Don't know if it'll be helpful. You don't have to use it, but it make it available. And if it does work out, let me know, because it's the first time I've tried it, and it may or may not be a good idea. So that's out there, and that's what that's all about. So moving forward, okay? And then Taha just mentioned in the chat, if you need any additional assistance, then he's got office hours as well, and you can also reach out to email to both of us to set up a time to meet. And so both Taha and I are available. And so I, have my normal office hours on Mondays and Tuesdays, and then occasionally I've met with students by appointment on other times. So if there's particular questions you have, then yes, feel free to definitely reach out. And all of our contact info is on Canvas there, right on the front page of the syllabus. Okay, so moving forward then, capping out the kind of like, so we've talked about a couple of different applications, and now we're going to go back to one more sort of a more theoretical perspective on simulation modeling, which represents which are these two terms that are often related, randomness and chaos, when in reality, these are not sort of as directly related as you might think. And so what we're going to learn about today is how randomness is actually a modeling tool that simplifies model building, whereas chaos is an apparent randomness that emerges from systems that aren't random. And so this will become more clear as we go through today, but the idea here is that randomness is going to be something you purposely add to models because you don't know how to make a deterministic model that is kind of precise enough. And so you can end up getting away with just putting in random effects instead, and that ends up smoothing over some of the uncertainty that you have about things that you can't quite pin down. Whereas chaos is you take a model that you thought you understood and you hit go, and you find out that it's a lot more sensitive to initial conditions than you originally thought. And it appears to sort of have kind of a random behavior, even though you didn't put any randomness in it. So in other words, randomness is actually going to be a good thing. It's going to make modeling easier. And chaos will end up being kind of a bad thing because it'll make modeling harder. So that's where we're going today, defining these two terms so that you can have some perspective when people use these terms and they're talking about these dynamical systems. And so we'll start with randomness, and randomness fits into the area of so-called stochastic modeling. So there's this term stochastic, which you may or may not be familiar with. And so we are going to sort of more formally define what that stochastic is. And so stochastic models are models that make use of randomness instead of deterministic rules. So rather than saying, you know, every time someone who is sick bumps into someone who is infected, then you're going to get, you know, 2 infected people. That would be a deterministic rule. Then a stochastic rule would be every time someone is sick, I bump into someone who's infected, half of the time you get 2 infected people, and the other half of the time you just have a sick person and an infected person. And so, you know, you end up having a simulation that sometimes when you run it, you get 2 sick people, and other times when you run it, you get a sick and an infected. And so that's what we'll, and this will become more concrete as we move on here. So the word stochastic, it sounds like a funny word. A lot of people think that it's just a synonym for random, but that's not the case. It turns out that that this is a Greek word, or comes from a Greek word for guessing or conjecturing. So basically, there was a, back when all models were kind of deterministic, then there were a set of modelers who wanted to put forward the idea that you could introduce randomness in a model, even though you didn't think the underlying system you were modeling was random. And so they didn't want to call them random models because they were afraid that people would say that, oh, well, but you're not modeling a random phenomenon. You're modeling a baseball moving through the air, and we don't view that as it's moving through a random trajectory. We kind of think that it's a deterministic trajectory, that we understand that trajectory. So why would you use a random model for that? And so the thought is, and I'll get to what I mean by conjecture here in just a second. Thanks for a question, Jordan. And so the thought was that instead of instead of calling them random models, they're going to call them stochastic models. And this stochastic so a conjecture is basically another name for a guess. It's saying that rather than trying to get a fine-grained understanding of all of the details that go into how something works at a microscopic level, we back up and we say, we don't understand everything that goes into it. And we are going to then admit that there's going to be uncertainty in the outcomes that we just can't account for. And so rather than trying to account for that with all these deterministic factors, we're just going to pretend that the model is random. We're going to make a guess that the model is random. And so, for example, my dog is not barking right now, but he could bark at any moment right now. And we could probably model all of the different ways that my dog, all the reasons why my dog would go and bark right now. And he could be hungry, he'd be hot, he could just want attention, all these different things. And we could then try to come up with a detailed model of how my dog's, Fritz's, that's his name, Fritz, how Fritz's brain works. And you know, and so we could come up with a purely deterministic model of how Fritz works. And then we could try to then use that model to say exactly when he's going to bark and exactly why he's going to bark and all those other things. But there's almost no way that I'm going to be able to properly come up with the parameters for that model. There's just no way that I can build an accurate model of how my dog works. But I can make a guess that he just barks randomly. And then I can sort of say, you know, on average, he barks 10 times a day. And then I just have to come up with like, well, how do I change that distribution of barks? So he barks more often at 5 o'clock than he does at noon, because 5 o'clock is closer to dinner. And so if I just change the distribution of when he barks, then I don't actually care about why he barks. As long as I get the random distribution of barking right, then I can end up getting a simulation which looks just like the real world. The real world might be deterministic. My simulation might be random, but my simulation outcomes look like very realistic outcomes. So I'm guessing that the real world is random, even when it's not, just because that makes the model easier. So it reduces our modeling burden. And we just talked about this boundary accuracy and structural accuracy. Now, I could list all those things I just talked about with Fritz. You know, it could have been Fritz's hunger state, his emotional state, his temperature. These are all variables that if I really cared about a deterministic model to get my boundary accuracy right, I would need to take all of those variables and put them in my simulation model. And then to get the structural accuracy right, maybe his hunger relates to his emotional state. So I'd have to link those things. So in order to get the structural accuracy right, I'd have to get all these links right too. And I would get a really ugly model that would be very difficult for me to defend as being an accurate model of Fritz. So instead, I throw all that stuff out and I say, I'm going to say that barking dogs, that's a random process. And there's a bunch of things that could go into it. And I'm not going to model those things. I'm just going to represent them by a random process. And that reduces my burden because I don't need to account for a bunch of things because they're already accounted for by the fact that they're random. I still have to justify my choice of random numbers, but I don't have to go into all of the details of what's going on underneath it all. So it's just a guess that it's random, but very often it's a good guess. So, so Jordan asked, is conjecture mean to go against logic? I'm not saying that this conjecture is, in some ways it is kind of going against logic, because you might be saying that I know that in the real world, there are deterministic processes that lead from a hungry dog to a barking dog. But rather than saying that I'm going against those, I'm saying that I do not want to keep track of all of the different reasons why a dog's going to bark. Instead, I'm just going to say that dogs typically bark around 5 or 6, and so I'm going to come up with a random distribution of barking that happens to have a higher average around 5 or 6 o'clock at night and a lower average in the other times, and then just go with that and forget about the details. So let's give sort of, get out of the dog space and think about something that we've looked at in a little bit more detail. So if we go back to lectures D1 and D2, this is when we introduced this bacterial growth example. And so in the bacterial growth example, we said that in real life, there is a single bacteria. It waits on average waiting time, W time units, before it becomes 2 bacteria. And so sometimes if I were to kind of look at the timeline of growth, then I can start with this 1 bacteria, and then there's going to be an event where it becomes 2. And then there's going to be some time that is maybe less than the average waiting time, where one of those bacteria becomes 2 again. And then after something maybe a little less than the average waiting time, again, we get another doubling event. But then we're going to get, we might just happen to wait longer than that average waiting time, and then we'll get another doubling time. And this goes on more and more. So in real life, we can say on average, they double every 2 seconds or every 2 hours. But that's only an average. And so in reality, they're actually doubling less than in 2 hours and more than 2 hours. So they're never actually doubling it exactly 2 hours. And so to make our modeling task easier back then, we took this reproduction event, which happened probably never in exactly W time units between events. And we turned that into a constant flow, where we just assumed they were always partially reproducing at a constant rate. And so each bacteria is reproducing at a rate of 1 over W, and then that means that as every W time units, then that constant flow of 1 over W accumulates another bacteria. So we have now turned the average behavior into a deterministic and constant behavior that goes smoothly over all time. And that's what made our models work. That's how we turned it into that. So we turned effectively bacterial growth into this bank account model, where we had a bank balance, which is like the number of bacteria that are in the bank, and then this partial flow every DT time units that came out of that was like interest being generated. And then, so then if we move from one compounding period to the next, then we got a new balance, a new principal here, and then that generated new interest over here, and then that process repeated. And so this perspective models the average behavior of the population, and it assumes that if we know what went on in one time step, one compounding period, one DT, then we can perfectly predict what's going to happen in the next DT, perfectly predict. So it's deterministic. And that's fine, that's a good start. But that just tells us how things are growing on average. Some Petri dishes are going to grow at a rate lower than average. Some Petri dishes are going to grow more than that. You're going to boom Petri dishes and bust Petri dishes. And so then the question is, how do we really model this variability? So what if we actually really want to know how consistent things are around this average behavior? So it may be that every single Petri dish grows at exactly the same rate, or it might be that I have some where they they're pretty much never grow, and others where they're growing super fast, and the average is a total fiction because there's just so much variability. So if I wanted to then use the modeling tools that we have been using so far in class, the kind of deterministic modeling tools, this would be like trying to explain all of the reasons why my dog barks. If I was to take this endogenous perspective, in order to ensure boundary and structural accuracy, I would need to know all of the details that go in to how a single cell of a bacteria works, and then how that then multiplies across all of these different cells. So some cells might be more dehydrated than other cells. Some cells might be closer to a reproduction time than other cells. Some cells might have had more nutrients available than other cells. And if I'm simulating 1 million cells, I might need to know how each cell is different from each other cell, so that I can show that some cells are about to reproduce and other cells are still waiting to reproduce. It would be really, really difficult for me to model the actual reasons why these bacteria vary in when they reproduce. And so the thought is, maybe I can get trajectories out of a simulation that look realistic, but don't require me to know all of the internal physiology of what goes on inside bacteria. And so the thought is, maybe, this is where the stochastic modeling comes in, let's get rid of all the details of that bacterial physiology and locomotion, and let's just replace it with random die rolls. Because if I think about it, there's a certain waiting time between one reproduction period and another. And if I would just roll, a 6-sided die, if I were to associate each side of that 6-sided die with a different random waiting time between reproduction events, I might actually get a trajectory for how long to wait between reproduction events that looks realistic. I roll a die, maybe it comes up a 6, and I just decide that 6, that corresponds to, 1.5 minutes. And then I might roll another die, maybe it comes up, I don't know, I can't see what's on top there, maybe it's 4, but it comes up 2. And I just say, well, whenever I roll a 2, it's not going to be 1.5 minutes, maybe it'll be 1.75 minutes. And then if it comes up a 5, well, I say, well, I'm just going to say that if it comes up a 5, it's 2.5 minutes. If it comes up a 1, I say, well, maybe then it's 1 minute, and then if it comes up, whatever's on top here, a 4, then maybe it's 3 minutes. So now it's almost like a board game, right? So I get some board game and it's got a die roll, and I flip to get to a particular spot. I look on the back of the card and it says, you have to roll a die now, and it has a table and it shows you all the different outcomes. And as I roll that die, it tells me which outcome I take. Well, that's what I'm doing now. I've gone from modeling the bacteria as a bank to modeling it like a board game. And so now I'm using the die to tell me, it's like a choose your own adventure, but I'm letting the die choose for me. So rather than having a deterministic rule where I always go one path, I just let the die choose. And it's like I'm given, whatever, 1, 2, 3, 4, 5 turns. And so on the first turn, I go one path, the second turn, I go the next path, and so on and so forth. And I end up getting something that overall, it doesn't look that different from reality. So in reality, there is variability in the time that you wait between these events. And now that I'm rolling the die, it generates variability as long as I have a realistic mapping from the 6 sides of that die to things that could happen there. I don't have events that are super, super long, and I don't have events that are super, super short. As long as I have 6 kind of prototype waiting times, and I'm just randomly choosing between them, then this schedule of waiting times looks pretty good. So the idea here is that the stochastic is describing what's going on in the model. It's not what's going on in reality. And adding this randomness to the model actually accounts for these omitted degrees of freedom in the model. So I technically, in order to really get this variability, I need to expand my boundaries so that they go around phenomena that are very difficult for me to model. And I am saying, I don't want to do that. So I'm going to keep my boundaries small. But then I've got this gap between what I actually need in my model to get the variability and the info I actually have. And to fill that gap, I add a little randomness. And if I get the randomness right, I will get a model that looks very, very much like the expanded model, but it's one that I actually can build with the information I have. So I'll give more examples of that, but I want to pause right here to see if there are any questions that have been generated so far before we keep going with this. Okay. All right. So I use this six-sided die example, but those of you who've ever played, more sophisticated board games know that, sometimes a six-sided die just doesn't cut it. Sometimes you need a 20-sided die. So the thought is that, okay, well, what if I had a 20-sided die? Well, now I can add a lot more variability. I can do a lot more interesting things with my bacterial waiting times. So I can actually even simulate a six-sided die with a 20-sided die. So I could say I roll a 20-sided die, like the one here on the left. And if I roll a 1 through 10, then I pretend like I rolled a 1 with a six-sided die. If I get 11 or 12, I'll do a 2, 13 or 14, 3, and so on, as I've sort of written down here. And so there's a question here. Would Dungeons and Dragons be a game that models stochastic behavior? I would say Dungeons and Dragons would be a stochastic model of real Dungeons and Dragons. So that's an excellent question. So those of you who play, Dungeons and Dragons, the reason you roll a die is because you don't have a real dragon available to fight against, and you don't want to fight a real dragon. But you assume that if you fight a real dragon, then you're going to win 75% of the time. Now, if you actually fight a dragon, I can tell you exactly why you won and all these things, like, oh, well, you jumped under the dragon, you dodged this. There's all of these little details. But when you're playing a board game, you don't have the dragon available, and you may not, even if you did have the dragon available, you may not actually want to go through with fighting the dragon. So you can say that, there are a bunch of different ways you can die from fighting a dragon. There's a bunch of different ways you can win fighting a dragon. We're just going to bundle all those things up together and statistically say 75% of the time, when you, with your skills, fight a dragon, you're going to win. And then you roll a die that comes up with a winning outcome 75% of the time. So Dungeons and Dragons is a stochastic model of a real world where dragons exist. That real world does not have to exist, but we can still have the stochastic model of it. So I hope that makes sense. Does that answer your question? And there's a lot of endorsements.
Yeah, that answers my question. I was just confused. I didn't know how you could pick a random variable, but that example of D&D does make sense.
Excellent, great. So yeah, 20-sided die you can actually use to simulate a 6-sided die. And again, if you're think about board games, then I'm sure those of you who played board games that ask you to roll multiple die or whatever, they usually have cards, and those cards might say, if you roll a 1 through a 6, do this. If you roll a whatever, I mean, it's exactly like what I've got out here. And what they're doing is they're setting up probabilities, because they want to make it really likely for certain outcomes to happen, but which maybe are the bad outcomes. But then the other ones that are like the good ones you're hoping will happen less often. So if you think about it, like rolling a 1 through 10 on a fair 20-sided die is going to happen 50% of the time. And then so the rest of these things are going to happen collectively 50% of the time, but each one individually is going to happen 10% of the time. And so this mapping of how I get from a 20-sided die to a 6-sided die creates an unfair 6-sided die. It allows us to emulate a die that comes up 1 half the time and comes up the other numbers equally uniformly among the other numbers. And I can then also simulate an unfair coin. So I can say, well, if you roll a 1 through 15, well, that's 15 out of 20. So 15 out of 20 times it'll come up heads, and only 5 out of 20 times it'll come up tails. So that's a 75% and 25%. If I've done that, or maybe I got that wrong. yeah, I guess I got that wrong. So it's 1/5. So I guess 80% and 20% maybe. Anyways, but the idea here is you don't even need a coin. You can actually get a coin out of a 20-sided die if you just map the outcomes of that die. And this is what we can do inside a computer. So it turns out that computers are really bad at randomness, but you can set up mathematical expressions that can generate strings that are not random, but they are difficult to predict what comes next. And so inside your computer, there are these so-called streams, and there's a bunch of them. And you can call up these random number streams, and every time you call them up, they basically roll from their version of a 20-sided die. But if you were to, shut down VinSim and start up VinSim and run them all over again, you get the exact same numbers out, the same pattern out. And so these are effectively defining patterns. So the pattern from stream 0 is different than the pattern from stream 1, and so on. But if you were to call stream 0, if you were to reset stream 0 and call it up again, you get the same pattern over and over again. So in order for two simulations to have different outcomes, so you stop VinSim and you rerun it, you would need to have VinSim use a different random number stream or start in a different place in the current random number stream. And so that's going to be one of the additional inputs to the random models that we'll build here, is this stream number, because we want, just like every time you play D&D, you don't want the same game to unfold every time. You want some variation. And so in order to get that variation, you have to put in different random number streams into your different simulations. And that guarantees that one simulation will have the same structure as another simulation, but different outputs. So to kind of get closer to what I mean, let's go back to thinking about bacteria. Here's the old way that we implemented bacteria. We had a deterministic population of bacteria, and we had an outflow of that bacteria. I'll call it deterministic deaths. And we put an average lifetime in here. And so the way we simulated, if we know the average lifetime and we know the current population, does anybody remember the formula that we would use in this flow, this deterministic deaths, in order to simulate a smooth outflow of bacteria as they die? What would be the formula that I put under deterministic deaths? Does anybody want to play or try a guess in the chat? Anybody?
Population divided by the average lifetime? Or is it never mind, I don't want to answer.
All right, so how many people think if you look in your participant list, and so right now, if your screen is full screen, if you go up to the top where there's a little either to the bottom of your screen or the top of your screen, you can turn on your participants list, and then there's little voting options under the participant list. So the suggestion was given as population divided by average lifetime. How many people like that solution, population divided by average lifetime? Seeing some votes coming in here. So you can vote yes or no if you think that's the right or the wrong answer. All right, waiting for votes to come in. Okay, seeing more and more votes. So far, all greens coming in. So yeah, I like that answer too. So I'd say that was a good answer. So I would say that the flow, what I would do here is population divided by average lifetime in this case. And that gives me the right formula where I've got the units of population divided by the time units, average lifetime. And so my outflow properly is in the population units divided by average lifetime. And I'd like to see all that support in the chat. That's great. So, so if I were to simulate this, if I started with 1,000 bacteria, then I hit go on the simulation and then look at what's in this deterministic population stock here, then I get this output where it starts high and then it smoothly decays along this exponential population. And every single time I run the simulation, that's what I get. And so this does not capture the variability that I would see in a real population. In a real population, some of them might actually kind of be up here for a while, and then they decay, and then they come back down, and so on. And then other ones might decay really quickly, and then they slow down. And so real populations won't always look like this, although their average might look like that. So that's what we would like, is to change this up so that we get variation. So every time we run the simulation, we get some different variation. So I now am going to introduce some slightly different ways to model this. And so I'm doing this in VinSim, but you can also do this in InsightMaker. And so the idea here is that I've got my now stochastic population stock, and I've now got this stochastic death flow, and I input into it a random stream. So this is just like a number, 0, 1, 2. So this is like the number of the die roll. This is like the die that you're giving it. And I'm gonna also need this time step, which is shows up as a hidden variable. So this is like your DT length. And then I still put in the average lifetime coming in here. Now let's see how all this works. So I'm gonna have a certain population at the current time. So I'm just drawing all of my bacteria at the current time. I've got no fractional bacteria anymore. I've just got a whole number of bacteria. And so the question is, which of these bacteria are gonna survive to the next time step? So basically, I'm going to want to then flip a weighted coin, just like I had, I don't know how many bacteria here, 8 or 9, maybe 9 or 10 different bacteria, it looks like 9. So imagine I had 9 players in a game. It's like me then flipping a coin. It's like almost a Russian roulette, where I go around and I ask, so each bacteria, are you going to survive to the next round? Are you going to survive to the next round? And we just see who's going to survive. And we end up coming up with these outcomes, where we get some bacteria survive to the next round, like the one over here. Other ones are selected for death and removal in the next round. And so we then can subtract the ones for removal, and that ends up being how we change the population. Now, how do I get this probability of survival? Well, I've got it up here, where I just need to design my coin. So remember, I can use that 20-sided die, or if I have like an infinite-sided die, it's even better. But if I've got that 20-sided die, I design that outcome table so that it comes up heads with a probability that I specify. And the probability of survival is going to be the time step, the DT, so I can maybe put DT here, divided by the average lifetime. So that's what's here. So this looks a little bit like our flow formula at the rate of, when we think about the flow per individual. So rather than saying that these individuals are continuously having an outflow of this, we're saying that each individual probabilistically survives to the next DT with this probability, DT divided by average lifetime. So with that, I can generate these outcomes, and then that gives me my next population in the next round. So because the way I did this, there's always going to be a whole number of bacteria. There's never any fractional bacteria. So that's what I would like to design. And so how do I implement that inside VinSim? And the way I'm going to do that, and then this is also similar for InsightMaker, there is this fancy function here called random binomial inside InsightMaker, inside VinSim, and there's again something similar in InsightMaker, that has a bunch of parameters that we're going to focus on a couple of them and not worry about too many of them. But this random binomial basically says for a certain number of coin flips, how many coin flips come up heads, given a certain probability of one of them coming up heads. So I put in my random number stream. So this is my 20-sided die from my Dungeons and Dragons into this parameter here. And then it will then generate outcomes according to that particular random number stream. And I am going to, and then coming out of it will end up being this number of heads given this many tosses. If each head comes up heads, or if each coin comes up heads with this probability, and I do these many coin tosses, then what comes out is the number of coin tosses that will come up heads. I see a question here. Is the coin example still considered stochastic behavior if there has to be either heads or tails? That is not very random. So the reason it's a stochastic model is because we don't know if each outcome is going to be heads or tails. We just know that there's a probability that they're going to be heads or tails. If we always knew that every tail was followed by a head and every head was followed by a tail, then it'd be a deterministic model. But we're saying that every DT, there's going to be a certain number of heads and a certain number of tails, and I can tell you roughly what the proportion will be, but I don't know if things will actually be exactly that number of heads or tails, and I don't know which ones will be heads or tails. So it's the uncertainty in the exact numbers that makes this random or a stochastic model.
And it was somebody's hypothesis would be like either half-half, and then they have to figure out if that's actually true or not.
Well, so that would be if I had a data set. So that you would sort of say you might have a hypothesis that, let's say, that a particular data set that you gathered from the real world was like that. You might say that in a group of students in a classroom, if you ask them whether they like artificial sweetener in their coffee, then you might say that on average, I don't actually think that students have a preference for artificial sweetener, and so half of them are going to come up and say that they like artificial sweetener and the other half are not. And I don't know which ones are which, but I'm going to get data after I ask all the students, and some of them are going to say I like it, some of the people are going to say they don't. And if I had 30 students, maybe I get 16 that say that they like it and 14 that say they don't. Well, that's not exactly half. But then I can use statistical methods like t-tests and things like that, and chi-squared tests, to then ask, well, given if the actual fraction was, it was a half and half per student, that some students like it and other students don't, but there's no like general preference that students are kind of could go either way, then how likely would it be that I would have gotten it in any selection of 30 students, 16 that said they like artificial sweetener and 14 that they don't, and then we could come up with a probability of that. So that's where I would kind of like test the hypothesis of what the probability is. When I go into building my simulation model, then I kind of say ahead of time, somebody's already told me that they have validated that the probability of liking artificial sweetener, or the probability of, or the average lifetime of bacteria is this particular thing, and they've already validated that. And so I now am going to say, given that I take that for granted, I'm going to simulate a more complicated system that's built on top of students that have an equal weight in whether they like artificial sweetener or bacteria with a particular average lifetime. So I'm putting those probabilities in as opposed to testing for those probabilities.
Okay.
Does that answer? Okay.
Yeah, thank you.
Great. So, like I said, this random binomial is a count of events during this time step. And so the randoms, so I have to divide by time step to turn it into a flow, because still VinSim is designed so that these little valves expect flows, and flows have to be sort of a number of events divided by time. And so that's why I'm going to do this random binomial divided by time step. So it looks a little weird, but that's what I'm doing. We're just turning a random outcome, how many events happen, divided by the time they happen. So that turns it into a flow. And so whenever in VinSim you implement these stochastic models, all of your flows are going to be divided by time step. And then inside the random binomial, I need to then tell it which die to use, which 20-sided die to use. And so if I were to rerun my simulation, I might put a different number in this. So the first time I run the sim, I put a 0 in. The second time I run the sim, I put a 1 in, and so on. And then that way, every time I run it with a 0, I get exactly the same output. Every time I run with a 1, I get a different output, but exactly the same output, as long as I start with a 1, and so on. So every time I run a new simulation, I want to change my random stream variable to get a different output. And then I'm not worried about these are some sort of advanced parameters that we just leave at 0 and 1. And then I put my number of tosses in here. So in this case, we're going to put the population size. So we're saying, given that the population is this big, that's kind of like how many tosses of my coin, or how many players are playing in this round. And then what probability does it come up heads for each player? So how likely are they to get the particular outcome that I'm testing for? And then I can set, again, these are kind of more advanced parameters, but I usually just set this bottom one to 0 and the top one to the same thing that I set number of tosses to. So if I take all of that together, then for this particular case, I get this expression where I've got this stochastic population comes in and it enters into this formula in 2 different places, just because that's just how this thing works. My probability of a death is going to be time step divided by average lifetime. And then my random stream allows for variability for different random streams. And then I divide by time step to turn this into a flow. So after I do all of that, then I can simulate this. And if I put both of them here, then the blue one is the outcome from the deterministic model. And this red line, which I'll zoom in on here, is the output from the variable model. And so I can see that they pretty much are on top of each other, but I get periodic variations from the blue line. So if I zoom in, I can see that the blue line is nice and smooth, as it always has been, but this red line starts to vary. And so this models a more realistic outcome. And I can notice that the red line is always whole numbers because it's actually a count of the number of bacteria. And I can run this for multiple input streams. And so if I rerun it by using a different stream number in that parameter, then I end up getting a bunch of different outcomes, and you can in each different color corresponds to a different stream number. And if I were to zoom in, then I get variation across here. So across the population, the average behavior matches the blue line. But now that I've actually simulated multiple populations, then I actually now can characterize how much variability there will be if I reran this experiment over and over again. So I get a measure of the true variability, and each outcome looks much more realistic than the original simulated outcomes. So the idea here is I capture realistic variability in the simulation. The upside of that is it's more realistic. The downside of that is I need to, instead of running one simulation as I did with this blue line, I have to now run as many simulations as I want in order to, until I get a good feel that I finally captured that amount of variability. And so I've really now turned this into an experimental or an empirical study where it's just like if I was running an experiment in the laboratory, I might have to rerun that experiment multiple times in order for me to get rid of the kind of variability that's in every experiment. Well, I've now added variability to my experiment, which means I need to run my simulations multiple times in order to make an inference from them. So, so that's sort of just for the bacterial case. And so then a tip is that you can actually make this generalizable to any one of your flow problems. You can just say that there's this formula that I've put here where you can put basically any flow rate that you've put in your deterministic models, and you can kind of cut it out like, and then paste it back in to this formula that I've specified down here. And this formula, which I won't go through all of the details, is very similar to mapping an infinite-sided die, like a die that has, you know, as side 1 all the way up to side 1,000,000, to mapping all of those finely enough so that you can simulate effectively any flow that you want. And so that is a way to take a generic deterministic simulation and turn it into a stochastic simulation that you'll have to run multiple times, but you'll start gathering the true variability in from your sim. So that's the end of our randomness part. And I want to flip over to chaos here for the last part of the lecture. But before we get into that, are there any questions about this basic idea of adding randomness to your simulation to make your sims more realistic without having to add a bunch more parameters? All right, let's see if everybody's awake. How many people feel like they feel good about that material and understood that to at least you know, a 75% understanding level. And hit yes if you didn't, then hit no in the participants list. And just seeing how many people are paying attention. All right.
I had a quick question.
Yeah.
So do we have to use this variability for all of the levels and variables in our models to make them more accurate, or only specific ones?
Oh, this is you don't, so on the short time scale of the course, you don't have to do any of this, but this is an option for you to do on the long time scale of thinking about simulation modeling. So just one of the tools in the toolkit. If you feel like you have a phenomenon that's just getting unwieldy and you don't have enough parameters to sort of fix, then you can get rid of some of those parameters and just replace them with randomness, and then come up with a random model instead of a deterministic model. It's just an option you have if you really think that if you want to either add realistic variability or get rid of some of your model complexity, but still have it generate interesting outcomes. Does that answer your question? For your final projects, I'm okay with final projects being totally deterministic. Sometimes people like to add randomness after seeing this lecture, and that's fine. I just want to make sure you're familiar with this, because real world models will frequently have randomness added into them, and because stochastic models tend to be very successful at capturing realism. I see another question here. I have a question. Why is the probability of survival equal to time step divided by average lifetime? So that is a good question. So the way to view that is, so there's a highly technical answer to that question that I'm trying to avoid, but the basic idea is that 1 divided by average lifetime, this is the average rate of the event. So we're saying per individual, the average rate that the particular event, let's call it death, happens, is going to be equal to 1 divided by average lifetime. You're going to get 1 death every average lifetime. And so, so if you weighted an entire average lifetime time units, then on average, you should get 1 death. Now, if you just looked at one individual, you just follow a single bacteria for average lifetime, then on average, if you follow that single bacteria and then you followed another single bacteria and another single bacteria, and you kind of stopped your stopwatch at average lifetime for every bacteria, if you then averaged across your experience, then you would have gotten about 1 death for that average lifetime. And so if you then, so you get like 100%. So the idea is that if you weighted average lifetime time divided by the average lifetime parameter, then that's going to give you 100% probability. So I guess I can put 100%. That will give you an 100% probability that a death will happen. Now, if you're not weighting the entire average lifetime, if you're only weighting DT, then you need to scale that probability down. And it turns out that if your DT is much, much, much smaller than your average lifetime, then that scaling happens in a linear way. And so your DT over the average lifetime is going to be far less than 100%. So that's, just remember 100%, that's just another way of me saying 1. And if that's the case, that your DT divided by AL is far less than 1, or your DT is far less than the average lifetime, then it turns out that the probability of seeing an event that happens on average every every average lifetime will be equal to just the fraction of the 100% time interval that the interval you're looking at is. So we're just taking the tiny time interval and we're asking how does that compare to the one event time interval? And the one event time interval is average lifetime. The tiny interval that our simulation runs across is this one. So the fraction of those gives us the probability that we're going to see this event. So it makes the event extremely rare, but that's kind of the point. Does that answer your question, or does that help?
Yeah, that makes sense. So then I just wrote it incorrectly. It's actually the probability of a death happening.
Yeah, you could, so I view the critical event in an average lifetime is death. And so 1 over AL is the probability that you will get a death. And so we normally expect one death in one average lifetime. And so DT over AL is the probability you'll get a death in a shorter period.
Okay, yeah, that makes sense. Thank you.
Great. Excellent questions, thanks. All right, any other questions about the stochasticity and the stochastic modeling? All right, so randomness is a good thing. It makes our lives easier. So what's a bad thing? Chaos is a bad thing. So chaos, roughly speaking, is an extreme sensitivity to initial conditions in models that do not have randomness. So these are models that we built and we want them to be highly reproducible. And so as an example, Fisheries Model, we've seen this, I don't know how many times this semester, so we should be pretty familiar with this thing. In this Fisheries Model, we have a carrying capacity of 4,000 fish. And I can run this Fisheries Model from different initial fish populations. So I start the initial fish population maybe low, maybe intermediate, maybe a little bit higher. It's not a fish population, so it's just the fish reproducing. And we know that they are all going to rise, logistic growth, and then they're going to level out at carrying capacity. So I've got carrying capacity up here at the 4,000 fish. And it doesn't matter where I start them off at, they are always going to hit carrying capacity. So if I jump ahead, jump ahead to say, looking at 32 years and ahead, then if I look at where the outcome is, then it's as if I can't tell what the initial condition was. So the initial condition just doesn't matter because they all end up in the same place. And so I have different initial conditions, and yet the system is so-called attracted to the same steady state outcome. The long run behavior is insensitive to the initial conditions. In the long run, it's impossible to tell the difference between any two trajectories. That's a good thing. It means that our models are sort of easier to understand. We don't have to worry that we set up the wrong initial conditions. We can just focus on what happens in the long time run. Everything will settle out, and eventually the long run behavior should be good. The problem is not all systems have this property. So here's a really simple system called the Mackey-Glass system. It's named after two people, Mackey and Glass, so it has nothing to do with glass, but it just has one single stock. And so I simulated this in Vinsim, and it has flows, an inflow and an outflow. It doesn't look that different than the fishery system. And similar to our outflow, you can almost think of this as being like a death flow and this outflow here. And you can think of this as almost like a birth flow. And there is a delayed version of the X flow in here. So we use one of those fixed delays. So I guess I could put, this is a fixed delay here, going back to our different types of delays, fixed and smoothing. And then the inflow formula here is given by this expression down here. So this is the inflow, and the outflow here is given by this expression here. And so I've just written our stock and flow diagram in the kind of more mathematical form, but otherwise you just implement this expression in the inflow, you implement this expression in the outflow, and you got this. Now, if I set up these parameters that are inside here, like beta, this beta here, tau, which is the delay here, gamma, which is this kind of death rate over here, n, which is an exponent in this shape here. If I set those up here, then something very interesting happens. So I'm going to set those up, and basically, again, I'm going to put the outflow is just going to be, so this is the formula for the outflow, and this is the formula I'm going to implement in the inflow. And this here is just a delayed version of the x that I've just put there as this auxiliary variable, fixed delay. So if I implement this in VinSim, and then I start it from different initial conditions, then I get some pretty interesting outputs. I get this pretty ugly trajectory, so it's not very smooth, like the nice logistic growth model. And if you kind of look at it, like, it makes sense that initially I would have some differences, but in the logistic growth model, then those differences kind of died off. And as you looked farther in the system, then you saw less and less differences. The opposite thing is happening here. Here, I can't tell the difference between my 3 different initial conditions, my 3 different initial x values. But as I look forward in time, it's almost like they get farther and farther apart. And I think I can, so different initial conditions. And if I zoom in, I can see that the different initial conditions, they start at very similar trajectories. So that's what I see here. But then they get more and more different. And if I keep going, they never quite land on top of each other. In fact, they just get more and more unique. So they get more distinctive as they go on. They maintain their individuality. It's almost as if I can tell what the initial condition was, you know, in an infinite time. It's like it keeps track of its initial condition in the trajectory. And so that means that the initial conditions really matter. These 3 different trajectories look like they're random. So it looks like they were started with different random number streams, but in reality, they were exactly the same deterministic system, just with slightly different initial conditions. So they appear random, but they're entirely deterministic. So that's a pretty ugly property, because it really then means that we need to get those initial conditions or these parameters really right. We can't be a little bit off. So, so then, you know, if we think back on it, this idea about delay, we know that from earlier in the course, negative feedback with a little delay can actually generate oscillations. And in some cases, that's what we're seeing here. So we see oscillations. So we saw kind of a rise. So this was sort of an initial rise and oscillations. So in some ways, it's a similar story that we kind of had, but at least before, these oscillations ended up landing in roughly the same place, or they would at least have the same shape as you went forward on in time. So what we're seeing here is that, that when you add these nonlinear feedbacks, so these ugly expressions like this, on top of delay, which we knew was already kind of problematic, then we get this phenomenon of chaos, where chaos is this extreme sensitivity to initial conditions, where the final trajectories, the steady state trajectories, don't look anything alike, and they can kind of be indexed by their initial conditions. So that's our first example of how we can get chaos. So there are questions about that before we go to the second way that we can get chaos in these simple models. I just want to emphasize, it's not random. It's totally deterministic. Okay. And in the second here, we'll see why I've been putting this image in these background slides. It relates to this chaos. All right, so is chaos just a property of delay? Just like delay typically causes these oscillations, does delay also, is chaos, is it also the path to chaos? And although delay can give you chaos, you don't actually need it for that. There is a relatively simple system that, here's one example called the Lorenz System, which has 3 stocks, and each stock has its own flow. So that's what I've got here. And so what you're seeing here is that each one of these things, these are the expressions that you would implement inside these flows. And some of them have parameters, like there's a sigma parameter here. You know, there's this rho parameter, beta parameter. So so that you could build this differential equation here on the right using this model here on the left. And that's 3 stocks and 3 flows. I mean, you guys are going to have final projects. All of your final projects are probably going to have at least 3 stocks. And so, so that means that all of your final projects could potentially look kind of like this. Now, if I set this system up with these parameters down here, this particular set of parameters, then it ends up looking like this. So then you can implement these in VinSim. So I take that expression and I put it in here. I take this expression, I put it in down here, and then I take this expression down here and I put it in down here. And if I were to implement that, that mathematics inside VinSim and then hit go for certain initial conditions, then what I get is, so I've plotted here, this is my trajectories of my Y stock, this is my trajectories of my X stock, and these are trajectories of my Z stock. And I've plotted them for 3 different initial conditions. And so we're just seeing all 3 being plotted here. And what we can see is, although you kind of see that they're all on top of each other initially in all of these plots, as we go further on in the trajectories, then we see that they separate. So again, we get chaotic behavior, extreme sensitivity to initial conditions. The initial conditions start close together, and then the trajectories get farther and farther apart as the system goes. They do not come back together. And so this lesson here is that even without delay, I can get chaos. Now, mathematically, we can show that if you don't have delay, you need at least 3 stocks to give you chaos. So chaos with delay with nonlinear feedback gives you chaos. Or if you don't have delay, 3 stocks can give you chaos. It won't always give you chaos, but once you have 3 stocks, you now are in the realm of possibilities that you might get chaos. Now, something cool about chaos is that if I plot things in this form, where I've got time going along this axis, and I've got my stock going along this other axis, then I get this ugly behavior, and it's hard to see the relationship between my stocks. And if I were to plot just one of them, so like just the Z stock, then it looks like I got this kind of like noisy behavior. It just like, it looks like there's no predictability to it. But if you see a trajectory like this, and it might be a trajectory you just see in data, like it might not be anything, you didn't generate a sim, but you just noticed that you took some data on a particular system. If you, instead of plotting the X, Y, and Z separately on a time axis, if you plot them together so that you plot, so this is like I'm plotting my X on one axis and say the Y on another axis. And so again, this is over here, X on this axis and Y on this axis. And so I'm grouping these points together by time. So if I were to like take, you know, a particular point here, that would correspond to a particular, that'd be like, if I were to go back to the previous sim, that'd be like saying, all right, I'm gonna look at time 24. Let's see where Z was at this time. Let's see at time 24 where X was at this time, and at time 24, where was Y at this time. And then I then go and I then say, okay, for then time 24, let's say this is time 24, then this is where X and Y were, and I'm plotting them together. So remember back to maybe high school, you might have learned about parametric plots. And that's what this is it's a parametric plot where I'm getting rid of time and I'm using time to group the points together. And when I do that, I have 2 different initial conditions. So this is one initial condition, and this is a different initial condition. And when I plot them together, even though on the previous slide, those 2 different initial conditions produce very different trajectories, when I look at how X and Y relate to each other, I get the same shape, even though I have a different initial condition. So when I see the same shape, that shows me that there really is deterministic structure in my system. It really isn't random behavior. But I can't see what that deterministic pattern is unless I plot the variables together like this and look at their relationship to each other, as opposed to plotting them separately over time. And this pattern that I'm showing here is what's called a strange attractor. And so I've got this is the system that I simulated. I see a question here. Wouldn't this correlate? Yeah, we're going to get to the butterfly effect here in just a second. So this is absolutely related to the so-called butterfly effect. Yeah. So so this that you're seeing this animation that's going on the right-hand side here is that same. Here's X and Y, and it hopefully looks familiar from that same from the plot that I had in the previous slide. We're taking that X, Y, and Z, and that little dot, that is a time point. And so this is bundling those things together, and it's taking this structure, this relationship between X, Y, and Z, and it's plotting them in 3 space. And now it's showing you this 3-dimensional relationship between the variables, and it's rotating it in these different planes. So you can see what X and Y look like, what Y and Z look like, what X and Z look like, and so on. And so this is the so-called Lorenz Attractor, and it does kind of look like a butterfly, but that's not related to the butterfly effect. And so these strange attractors. So remember, in the sigmoid and the logistic growth formula, we said that the steady state population, that was the attractor of the system. Or if a system that just has a simple delay, if it rises and then oscillates, then this oscillatory behavior is the attractor of the system. So in chaotic systems, we can't see in the time picture what the kind of natural structure is. It doesn't look like a flat line or a nice oscillation, but when we plot the variables together, then we see this structure, and that's this strange attractor. And that's these chaotic systems typically have these really interesting strange attractors. And so this clear pattern doesn't become clear unless you put the variables together and look at them simultaneously. And so if you saw apparent randomness in one variable and concluded it was random before you looked at how the variable related to all the other variables, you'd be making a mistake. And so this is a frequent thing when people take time series data, like on traffic patterns, for example, and they say, oh, there's just random fluctuations in traffic. So we've got to then simulate in our models, we got to put randomness in there because we don't really understand what's causing these traffic fluctuations. But when you plot the traffic fluctuations together with other variables and other data, then you start seeing that relationship. And then you may be that you can actually build a deterministic model that generates all these ugly fluctuations without having to add any randomness in. So, I mean, you take all this stuff together, and so here's a quote from Lorenz, the same researcher who came up with the Lorenz Attractor and the Lorenz System, is that a definition of chaos is when the present determines the future, but the approximate present does not approximately determine the future. So present determining the future, that means that there is a simple system that we can draw in VinSim that says how X affects Y affects Z and back. But even though we know at that level, at that microscopic level, how X affects Y affects Z affects X, we can't then predict based on wherever X, Y, and Z are now, what's going to happen roughly in the future. So, so that's chaos, when your predictability breaks down as you go farther in the future. The weather is a chaotic system. We can only predict for a very short amount of time. We have no idea what's going to happen later. It's not that the weather is random, even though we might like to simulate it with random. It has so many variables coupled in these nonlinear dynamic ways that it's chaotic. And that then allows us to sort of, we're getting kind of close to the end here. And the last slide is this goes back to this butterfly effect question. So you may have heard of this butterfly effect, and some people incorrectly say that the butterfly effect means that a butterfly flaps its wings in Africa and causes a market to crash in the United States or something like that. That's not the butterfly effect. It's not that the butterfly is flapping its wings and like with that little puff of air is causing things to happen. It's that in a universe where the butterfly's wings are open, the markets may be in a bull market. But in another universe where the butterfly's wings are closed, the markets may go into a bear market. It's not the flapping that causes the markets to change, but it's the extreme sensitivity to the initial conditions. So it's the fact that this type, in most models, you wouldn't think that it mattered whether you got the initial conditions of whether the butterfly's wings were open or closed. But in chaotic systems, you have to get every initial condition just right, because a slight incorrect choice of initial condition can lead to very different effects later on in time. So it's not that the butterfly's wings are flapping, it's that universes where butterflies are in one configuration are going to be very different in the future than universes when they're in a different configuration. And so there's a mention in the chat that some of these visualizations, these strange attractors, look very artistic. And so this visualization here, this is another attractor, by the way, that I've put behind these slides, another 3D visualization of these. And if you, so there's a bunch of these programs like this Mandelbulber that is, it's a software program that allows you to go through these different categories or these different libraries of these chaotic systems and run them. And it basically is running its version of VinSim behind the scenes. And it will then generate these things and have nice ways you can visualize and play with them and then turn them into art if you'd like. And this here, yeah, this is an attractor. This thing here is a strange attractor of a particular system that, and so, yeah, like I said, it looks pretty cool. It's been colored in funny ways, but yeah, this is a dynamical system that you could simulate in VinSim without any randomness. And if you plotted all the variables together, you would get this structure that came out. All right, so are there any questions about this chaos stuff? All right. So we're at 4:15, and so Brooke puts I'm going to endorse a video, even though I have no idea what it is, and I hope that that's not going to get me in trouble. But there is a link there in the chat about chaos, and so take a look at that if you'd like to have some more info. I also, I think, have an auxiliary lecture where I just go over this content on the Canvas site if you'd like to hear me present this in a slightly different way. All right, so looking forward, so we're at 4:15. I don't want to keep you guys too long. So keep working on your projects, because the next class, we're going to have an open lab. So you put in your breakout rooms, and there's nothing due. So no attendance or anything like that, but it's just your opportunity to work with your group and to then, as I bounce around and Taha bounces around, and try to get help from us. So try to come with your projects already to the point where you have questions to ask, and then that we can hopefully be a little more effective. And then we've got one last sort of lecture activity that's next week, and then we'll be at the last week of class. And so at the last week of class, we're going to have a final exam review on that Tuesday. Your final project presentations will be due Wednesday by 5 p.m. And then you'll get peer review assignments at 5 p.m. after all of them are turned in. And then you'll have a final exam opportunity Thursday. And we've talked about, you know, and so it won't be during class, but it'll be kind of due during then. And then your final report will be due Saturday, as well as your peer reviews. And then if you want to do a retake, then there will be a final exam retake during finals week. So that's what's going forward. So the attendance exercise, and then I'll hang around here till 4:30 in case anybody has any other questions. Your attendance exercise today is what is a simple definition of the word chaos? So put that, and I'll put that in the chat. And then for now, if you'd like to head out, feel free. I'm sorry, it's 4:17. I didn't mean to keep you a little bit later. And then otherwise, if anybody else wants to stick around and ask a few more questions, I can leave the recording on until we're done. And then once everybody's gone, and I'll close the room. So are there any questions that I can cover?
Just
Again,
about
feel
that
free to
final exam, it's due before class that day. That's what you said?
No, so no, I didn't mean to say it that way. Is that, I guess what I'm saying is that normally, if we were in class, it would be during the classroom experience. So what I'm going to do is I'm going to give you 75 minutes, and you'll be able to start it ahead of time, but I'm probably going to make it, you have to start it by like the end of that night or something like that. So so that's my thought, is that I'm going to make it due, the pre-take is going to be due the Thursday, but I'm not going to force everybody to take it at a particular time on Thursday. So it'll pretty much be like anytime that Thursday you could take the final, and then, but once you start it, you'll get 75 minutes to finish it.
Okay.
And similarly for the retake, which will be during finals week, which I think is on a Tuesday.
So we can take it that day during class period then?
You can, absolutely. Yeah, so it'll just be available. So if it's good for your schedule to just show up at 3 and take it, then that's fine. It'll all be on Canvas, so there will be no class.
Okay.
Any other questions?
And when are we practicing that lockdown browser? Sorry.
Oh yeah, so I'll put together like a 1-question assignment, and I'll try to do that this weekend, and then that way you're sure that your lockdown browser is working, and that'll like be like a fraction of your, maybe like 0.5% of your final exam grade or something like that, and then that way it kind of adds a little bonus to it too, and gives you incentive to do it.
The midterm practice is basically what our test is going to be like then? The final?
The final is modeled after the midterm. So, and I wanted to make it in theory fitting within a 75-minute period to allow for the retake. So two of them will be the same like length. I might give you guys a little extra time, but it'll be designed for 75 minutes. Any extra time I add will just to accommodate for any technical issues that might come up.
Okay, thank you.
Oh yeah, and you will, I can give you a sheet. And so in the lockdown, you're gonna like, I'll give you instructions, but you'll like hold up your sheet and show it. And then you'll also kind of like scan and make sure there's no other resources. So yeah, I think I've got, we'll go over this in the review, but I think I'm allocating 1 sheet double-sided. Any other questions? Okay. All right, so if there are no other questions, then I will, thanks for the feedback in the chat. Then I will end the recording and close the room. So last call here.